Hello and welcome to Beamer Folk. The other day I started working on a project that needed a 10 kilohertz clock frequency and a negative supply. The negative supply didn't really warrant a 0 plus or minus power supply. It was just a couple of op amps for signal processing, and so I wanted a localized negative supply voltage. And there are several ways that you can do this. You can buy a little inverter that will mirror the supply voltage, but those kind of seemed elaborate. And as I wanted a clock frequency anyway, I started looking at the ubiquitous 555 timer, and I was able to derive a perfectly adequate mirrored supply voltage in the negative from a 15 volts DC supply, and this is the circuit you see here. I don't know that I should go into the fine details of a 555. There are a billion sources of information on that out there on the internet, but nevertheless I shall put a link to a 555 datasheet for you to peruse at your leisure. I might just go through the pins, but anyway, I'll do that in a second. In principle here I've got a battery, but in fact that's really a 15 volt supply, which is at this point here going into the 555, and the output of the 555 drives a diode pump system using two capacitors and two diodes. The two diodes incidentally are the 1N916, 914 signal type of diodes, and as such, when you look at the negative supply which it creates, you've got a 1 volt drop from the plus supply translating, mirroring into the minus, and that's simply because of the drops across the diodes and the saturation offset of the output transistors of the 555. The 555 can incidentally drive a source or supply 100 milliamps. This doesn't use anything like that, and the load I've put out onto a variable control here, a slider, and at the moment it's drawing 3.9 milliamps to a supply current from the supply of somewhere between 4.5 and 8, so on average that'd be just about 7 milliamps. So it's quite good, and I'm quite pleased with it. The frequency here is, if you look at the display down here, is a little high. I could do with lowering that, and how I do that on this excellent simulator circuit. It's the I've used it before on my projects, and it's the falstead.com online simulator. The 555 is in a astable multivibrator configuration, charging through these two resistors here and this capacitor of 1 nanofarad here. You've got two 56Ks, which if you allow from the discharge pin here, if you allow the discharge to discharge through this resistor and charge through these two resistors, the two resistors representing 112K and the discharge of 56K, you would see that the duty cycle would be probably about 33%. As you can see here, it's actually 51%, and how I've derived that is by putting a diode across this discharging resistor here, so that when the capacitor is charging from the supply, it only charges effectively through this one resistor here, and when it's discharging, when the 555 is discharging, it only discharges through that resistor there. Probably go through the pins of the 555 just in case somebody's not familiar with them, but I'll stress you need to really look at the data sheet. Start off with a supply pin. You've got a supply pin here of pin 8. It's linked through to pin 4. That's the reset pin, and it's disabled by linking it up to supply. There's the discharge pin, which effectively discharges the timing capacitor. You've got a negated trigger pin here and a threshold pin. The trigger pin, if the capacitor is less than a third of supply is 5 volts based on 15 volts. If the capacitor voltage is below 5 volts, the trigger will trigger, making the output go high. When the capacitor reaches 2/3 of supply, which on a 15 volt supply is 10 volts, the threshold will be reached, and then the output will go down to 0 and the discharge pin will go low to discharge through that resistor. There is a control pin here that's effectively decoupled and disabled via this small 100 nanofarad capacitor, and of course you've got logically pin 1, which is ground, and here's the output pin here, and that's effectively a 555 for you. And how successful has it been? Let me drop the frequency down to my preferred 10 kilohertz or thereabouts. It's not ultra critical, but at 11.5 kilohertz it's a bit high. So I go into edit, and let's say let's add another 100 puff to the charging capacitor and apply that. And you can see that it's actually moved the frequency down to approximately 10 kilohertz. And in the final circuit, I could probably trim it a little bit better than that. What I would do, I will put this circuit onto a breadboard and demonstrate it in practice and see how it matches this simulation. Let me vary the load. I've got at the moment just under 4 milliamps. Of course, and you're looking at the test point here of 13.8 volts. If I lighten the load right the way to the end of 6K, say, you've got 13.9. There's not a great deal of difference between that and 4 milliamps, so it's holding quite well. And I try and get up to, let's say, 5 milliamps. That's 6. Let's get to a little bit less than that. There we go. So there we are, there's 5 milliamps, and you can see that we've got 13.8 still. Let me move it to 10 milliamps. I don't think this circuit is going to hold on 10 milliamps. A little bit more of a load. Here we go. There we are. 10.1 milliamps being drawn from the minus 14 volts, and in fact it's looking as minus 13.8 volts. So it's not doing too bad. That's certainly enough to drive an LED into brightness. And for our 10 milliamps here in the negative, it's drawing from the 15 volt supply somewhere between 13 milliamps and let's say 19 milliamps. So you're looking at about a 16 milliamp supply from a 15 volt supply voltage. And that's more or less it. All I've got to do now is implement it into a breadboard and see how it works. There are a couple of points I should have added to this. One is that as an interesting quirk of 555, that because it uses one capacitor for timing, when you first power up a 555, the pulse width is slightly longer than when it's operating in continuous frequency. And the reason is that the two threshold voltages of 1/3 and 2/3 is only correct after the first pulse. The first pulse has actually got to rise in voltage from 0 volts to 2/3 before the threshold discharges the capacitor, And because it takes a longer period of time going from 0 volts to 2/3 as opposed to 1/3 to 2/3, the very first pulse you get from the 555, even though it's in astable multivibrator mode, will always be longer. Secondly, of course, I could have improved the voltage drop on this negative voltage by putting Schottky diodes in here, or indeed if I wanted to go to the trouble of using a synchronous rectifier here, I could have got this negative voltage to very close to the plus 15 volts. But there was no point in me doing that, going to that effort, simply because most op amps, I don't know of an op amp that doesn't do this, but I'm sure there are a few out there, and that is an op amp doesn't really object to the plus and minus supply being asymmetric. In other words, of a different value. They seem to tolerate that quite well. The only problem you might have is if you want the output of an op amp to actually drive down to minus 15 volts. Well, as you've only got just under minus 14 volts, it would never achieve that. Thirdly, if the op amp is driving a lower impedance load, in other words, if it's driving a power device as opposed to, let's say, signal processing, if you try to extract through the op amp a current which exceeds 10 milliamps, then obviously this negative supply voltage inverter, mirroring inverter, will not be able to supply that, and the op amp would of course collapse. But what you can do is ensure if you drive any significant current from the op amp or your circuit, make sure it is in the positive so that the op amp is deriving its current and power from the plus 15 volts and not the minus 14 volts DC. I hope that's been of interest to you.
So here we are at the breadboard without a single piece of bread in sight. I've assembled the components as described on the simulator to the breadboard. They are identical, except that I've made an addition of a decoupling capacitor, a 1 microfarad, as per data sheet, between the positive pin, which is pin 8, and the negative pin, which is pin 1. That's the only thing I've altered. Oh no, in fact I've altered something else. I've put a little padding capacitor across the 1 nanofarad of I think 150 puff, and that's brought the frequency into about 10 kilohertz. All that remains is for me to power it up. There we are. The blue LED is the negative supply. The meter reading is reading the volts of the negative supply. The positive supply is 15.02. The white LED shows the 15.02 positive supply, and the blue LED shows the negative supply. And as you can see, it's perfectly working. It's at 10 kilohertz. The 555 is the transistor version. You can, of course, use a CMOS version, and that would also extend the frequency in which you can switch at I think about 2.7 megahertz. As it is, the transistor version I think only goes up to about 100 kilohertz, and as I've got this at 10 kilohertz, it's well within. And there we are. The load, incidentally, is asymmetric in the sense that I've got a 10 milliamp load on the negative supply and a 2 milliamp load on the positive supply. And that's about it. There isn't much more. I will do an efficiency calculation at the end here, just for us to get a grip as to how good or bad it is.
This is Beamer signing out for now.